You can take off.
Okay, sir. Thank you. Thank you, my dear sir. Hello, Tatelo. I think you are the only one who joined the lesson. Hello, how are you, sir? Sir or ma'am?
I'm good, sir.
Cheers, man. I think now is our time to start, and we are already late with that 1 minute. So we can just dive into the lesson. Oh man, my bad. I forgot to introduce myself. I'm Mr. Musetsona Makhema, but you can just call me Tlo. I joined the team for mathematics. I'm just going to be with you all for mathematics. But I was instructed to start with Euclidean geometry today. So today we are going to look at Euclidean geometry, one of the most interesting topic I've ever seen in high school. I used to love Euclidean geometry a lot. So I would advise you to know Euclidean geometry a lot because you're going to need it a lot in grade 11, also in grade 12, because it takes a lot of marks in paper 2, about 50 marks, of 150 or 40, it ranges there. So you can also check it out from ATP, Annual Teaching Plan. So without wasting any time, we can just dive into the content that we are going to focus on today. Then, which is this. Just hang there with me. Then mind action, grade 11. Right there. Can you see my screen there, sir?
No.
Okay, maybe I didn't share. Let me try to share. Share the screen. Share now. Can you now see?
Yes, I can see now.
Okay, you see my textbook right here on the screen?
Yes, I can see the textbook.
Okay, thank you, sir. So right here in front of us on the screen, we have chapter 8, Euclidean geometry, revision of earlier concepts from grade 10 to from grade 8 to grade 10. I would say, I think you started this Euclidean geometry from grade 7. Maybe they forgot that. So we will first focus on the lines and the angles. Then just go to the triangles. After triangles, we will go to circle geometry. So what we are just going to talk about now is very, very, very important in maths. As all, you need to know it. It's going to help you a lot in grade 11, also in grade 12 next year. So let's first look at this first structure of mine here. This one. They are saying an adjacent supplementary angles. They are saying in the diagram, angle B1 and the angle B2 is equal to 180 degrees. So we can see this horizontal straight line in this diagram. Then we can also see that inclined line from B going with towards northeast. So that line divides that angle 180 degrees into two angles, such that when you add those two angles, they add up to 180 degrees. They are supplementary. That is what is meant by supplementary, a term supplementary. Supplementary means that they add up to 180 degrees. So please just let me know if I move too fast or too slow to just keep the pace to accommodate you in the room. So in this diagram, let me just emphasize this. They are letting us know that when you take angle B1, you add angle B2, you are definitely going to get 180 degrees. Then remember, Euclidean geometry, actually maths, I think in general, you don't have to assume. You need to work things mathematically in a correct way. So in Euclidean geometry, I can say maybe the backbone of Euclidean geometry is reasoning, because without the reasoning, you are not going to pass Euclidean geometry. Because in order for you to pass, you need to get full marks. In order for you to get full marks, you need to put the statement and the reason. So the statement for this diagram is that angle B1 plus angle B2 is equal to 180 degrees. Then that's a 1 mark. If this was a 2 mark, another mark will come from a reasoning. That the reasoning being angles on a straight line are supplementary. Then we know that supplementary means they add up to 180 degrees. Then you get your full 2 marks. Then we move to the other diagram right here in front of us, the screen. They are saying angles around a point. In this diagram, the small a plus the small b plus the small c is equal to 360 degrees. This is the angle around the point, the revolution. If you maybe put your finger at the 12 o'clock on the watch, you go 11, or maybe even if you can go clockwise 1, 2, 3, 4, 5, 6, and then your finger goes back to 12 o'clock. That's a revolution, and then you just made 360 degrees. So in this diagram, they are saying if you add angle A, angle B plus angle C, you are definitely going to get 360 degrees as an angle. Then your reason going to be angles around a point, or the revolution angle. Then we can proceed to this one right here, right below that one of the adjacent supplementary angles, whereby we are going to talk of the vertically opposite angles. They just demonstrated it in a simple, graphically set, whereby there's those two lines that forms an X shape. And then they're saying vertically opposite angles are equal. In this X of ours, those angles that are equal, they need to be opposite each other. You can't say that plus inside the circle is equal to this black dot, big one. You can't say they are equal and then give a reason of saying vertically opposite angles. No, on your X, they need to be a vertically opposite, not adjacent angle. So that's a vertically opposite angle. Then we move to corresponding. After corresponding, we are going to move to alternate angles. After alternate, you're going to go for co-interior angles. So this is what applies to these three parts. For corresponding angles, alternate angles, co-interior angles. I need you to know this forever. Not only today, not only next month, not only for your final, because even next day you're still going to need this and you're going to use it a lot. So for corresponding angles, alternate angles, co-interior angles only applies if there exist parallel lines in the diagram that you are working with. I hope it makes sense. Only if, when you look on the diagram that you are working with, there exist some parallel lines, then you definitely can use corresponding angles, alternate angles, co-interior angles. But if there is no parallel lines in the diagram that you are working out with, then you can't use corresponding angles, you can't use alternate angles, you can't use co-interior angles. Because remember, I said we don't assume, we state what is mathematically correct. And then we support using the reasoning. Okay, thank you. Then now let's move to the corresponding angles. They are saying here, if the line AB is parallel to the line CD, then the corresponding angles are equal. Then right here in front of us, we can see that angle X is equal to angle X. That's a statement. Then you put a reason, corresponding angles. Then your reasoning, if you're working with parallel lines, is accompanied by the parallel lines. You state them. AB is parallel to CD. Same applies with the alternate angles. If the line AB is parallel to the line CD, then angle X is going to be equal to that angle X. Then I think to just make things simple, you just need to remember, just maybe imagine that Z maybe on your diagram, then know that these angles are equal. Know that those angles are equal. Your reason is going to be alternate angles. Then it's going to be accompanied by the parallel lines, that AB is parallel to CD. You can't just say angle X is equal to angle X and just leave it like that. No, you won't get full marks. You need to show off as a mathematician. State those parallel lines. AB is parallel to CD. Same applies with co-interior angles. With co-interior angles, it's a bit different from corresponding angles and alternate angles, because we can see that with corresponding angles, we had this F shape, whereby this angle was equal to that angle. And then, okay, this angle right here is equal to this angle right here. Same applies with alternate angles. We said here, this, what's happening here? Sorry. Let me just do this. We said this angle is equal to this angle. But with co-interior angle is a bit different. There are no equal angles. But those angles that are inside that U that we are going to focus on, let's say this U. Let's say this is our U that we are talking about. Then if you take this angle that is red there, you add this angle that is here. They are not equal with co-interior angles. They are different with size. But if you add those two angles, they are supplementary. They give you sum of 180 degrees. Then you state your reason that they are co-interior angles, and you state your parallel lines. AB is parallel to CD. That's all you need to know with parallel lines. Then, and just before I can leave that part of parallel lines, I think I have to emphasize this before I can proceed. Remember that you can only use these three parts: corresponding angles, alternate angles, co-interior angles, only if there exist some parallel lines in the diagram that you're working out with. These three reasons. If you are not given that some two lines are parallel there, don't assume that some lines are parallel just because maybe one is above another. You can't assume. Then let's move to the other part of geometry, whereby we are now going to focus on the triangles. With the triangles, we know that there are several types of triangles: scalene, isosceles, equilateral, right angle triangle. So you need to know the properties of each and every triangle, because you are going to use that a lot in geometry, and that is going to help you a lot. So firstly, let's look in this scalene. They are saying scalene, no sides are equal in length, meaning scalene is a triangle whereby all the sides of the triangle are unequal. If the other one is 4 units, the other one is 6 units, the other one is 7 units. You can't have 2 units, 2 units, and 4 units. No. Scalene, all sides of a triangle are unequal. Then now, let's move to an isosceles triangle. Oh, I love this triangle. We are going to use it a lot. So isosceles triangle is a triangle whereby two sides are equal and base angles are equal. Those base angles, note that they are opposite those equal sides. This angle right here is opposite that side, and this angle right here is opposite that side, and those sides are equal. Therefore, this conclude by saying these angles are equal. Angle A is equal to angle B. Just like that. Then reason being angles opposite equal sides. Then that's what you need to know with a isosceles triangle. Then we can move to the other part. We have equilateral triangle right here on the screen. Equilateral, I think you can just tell from the name. Equi, meaning there's something that is equal right there in the triangle. So they are saying all three sides of this triangle that we are talking about are equal. And all three interior angles are equal. And those three angles, note that they will always be 60 degrees if we are talking about equilateral triangle. Those 60, they will add up to that 180 degrees that we talked about when we said the sum of interior angles of a triangle are supplementary. So we can move to right angled triangle. You know from grade 7 when you learned about angles that you had acute angle, obtuse angle, or right angle, straight line, reflex, revolution. That we said an acute angle is an angle of the size that is less than 90 degrees but greater than 0. That is an acute. Then we have right angle. Right angle is an angle of 90 degrees with the sides. Then obtuse angle is the angle that is greater than 90 degrees but less than 180 degrees. That is obtuse. Excuse me. Then the straight line is just a line with the size of the angle of 180 degrees. Then the reflex angle is the angle of the size that is greater than 180 degrees but less than 360 degrees. And the revolution we have talked about earlier on when we were talking about the angles around the point, that the revolution is 360 degrees. Oh, then the right angled triangle, you can tell from that name, right angled, that there must be some right angle there, which is 90 degrees. So they are saying right angled triangle is a triangle that have got a 90 degrees within the one of the triangles that are within the triangle. So we also have this note right here. We are going to use this a lot. Let me just, what's happening now? Don't run this. Okay, no, it's fine. Let me just leave it out. But I wanted to just highlight this part for the sum of the angles of a triangle. That if you take that small a, you add small b, you add small c, you are going to get 180 degrees. Reason being, the sum of interior angles of a triangle are supplementary, or the sum of interior angles of a triangle add up to 180 degrees. That's what you need to know. It's very, very important. Then we come to this one, whereby we can see we have this triangle, and then on the base of this triangle, there is a line that is produced towards east or towards to the right. That line, and then it forms some other angle between the side of a triangle and the line, which is the angle small c. Then there's this theorem in geometry that says that angle small c will be equal to the sum of that inside A and B. Reason being, exterior angle of a triangle is equal to the sum of interior opposite angles. Then we move a little bit to this Pythagoras theorem, one of the very, very powerful theorem that were invented a long time ago. So note that, I noticed some people use Pythagoras theorem anywhere they are required to find the size of the side of a triangle, even if that triangle is not a right-angled triangle, of which that is wrong. Pythagoras' theorem only applies on a right-angled triangle. So on a right-angled triangle, you're going to have a hypotenuse side. What is a hypotenuse side? Hypotenuse side in a right-angled triangle, in this case, is going to be this side, AC. It's our hypotenuse. It's just going to be our hypotenuse. So this formula right here, you can see it's AC squared is equal to AB squared plus BC squared. Then AC is that hypotenuse that we talked about. And then hypotenuse, the square of the hypotenuse, will always be the subject of the formula, will always be subject of the formula. That will always be equal to the sum of the squares of the rest of the sides, which is this one and this one. I hope it makes sense. You'll just shout out if you don't understand. Then from there, we move to the congruency of the triangles part, whereby we have 4 conditions that can be satisfied in order for you to show that maybe 2 triangles are congruent. Condition 1 is saying that 2 triangles, there are those 2 triangles, just next to the statement that I'm reading now. 2 triangles are congruent if 3 sides of one triangle are equal the length of the 3 sides of the other triangle. If these 2 triangles have got equal sides, then those triangles are going to be congruent. Then side, 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 because we focused on sides and there are 3 of them, side, side, side. Okay, then we can proceed to the second condition. They are saying here, 2 triangles are congruent if 2 sides and the included angle. Now they are talking about 2 sides and 1 included angle of the first triangle. If those 2 sides of the first triangle are equal to the other 2 sides of the second triangle, and that angle that is included on the first triangle is equal to the other angle that is included in the second triangle, then those triangles are congruent. Sorry, a bit, hello? Hello, can you please close your mic, or are you shouting out something? Okay, I think they can't hear me. Let me just continue. So, condition 3, we are going to have 2 triangles. These 2 triangles are going to be congruent if 2 angles of these 2 triangles are equal, and one side of the first triangle is equal to the other side of the second triangle, then those triangles are congruent, which is going to be angle side angle. Then you go to the last, which is the 4th condition of the congruency. They are saying 2 right-angled triangles are congruent if the hypotenuse, and we know what the hypotenuse is, if that hypotenuse and the side of one triangle is equal to the hypotenuse and the other side of the other triangle, then those triangles are congruent. Because remember, these 2 triangles are right-angled triangle. Already we have that angle, which is the right angle, is equal on both triangles. Then we focus on the other 2 sides. Then therefore those triangles are congruent. Then we are done with the conditions of the congruency. We can just proceed to the midpoint theorem, of which I think we are also going to use this in grade 12. It will be wise for you guys to just ensure that you keep this in your minds. The midpoint theorem, in this case, we have got 2 triangles here, you can see. but I think they are similar. It's just that the other one have got two parallel lines, the other one doesn't. But let's first focus on the first one on the left, triangle ABC. And then we can see in this triangle, we are given that AD is equal to DB. And again, AE is equal to EC. Then if that's the case, then that implies that DE is parallel to BC. And then DE will be half of BC. That's what this theorem says. If you are given this triangle ABC, and then the line is drawn there, the line DE in this triangle, such that AD is equal to DB and AE is equal to EC. That implies that this line that you have drawn now, DE, is parallel to BC. And that line DE is the half of BC. Same applies with this other one. It says if AD is equal to DB, and then now in this case, if it is given that DE is parallel to BC, you should know that AE is equal to EC, and that DE will be half of BC. That's what you need to know with the midpoint theorem. Then from there, we can just proceed to the properties of the quadrilaterals. I mean, I've got a lot of quadrilaterals. You need to know the properties of each and every quadrilateral because you're going to use that a lot in this geometry. We're going to use parallelogram, we are going to use rhombus, we are going to use rectangles, we are going to use squares, we are going to use trapezia, etc., etc. So firstly, let's just look at this parallelogram that we are having on the screen now. A, B, C, D is a parallelogram. You may assume the following properties. So I say you don't have to assume. You have to know these properties. You don't have to assume them. You have to know that it is a fact that the opposite sides of a parallelogram are equal. And the opposite sides of a parallelogram are parallel. Meaning in this case, AD is parallel to BC. And AD is equal to BC. Same applies with AB and DC is equal, they are equal. And AB is parallel to CD. That's what you need to know. It's a fact. Then same applies with the angles. Opposite angles of a parallelogram are equal. And let me just highlight this. This angle right here is equal to this angle here. They are equal because they are opposite angle of a parallelogram. This angle here is equal to this angle here. Opposite angle of a parallelogram are equal. Then we also have these diagonals here, AC and BC. Then we can see that they intersect at E. And AE is equal to EC and BE is equal to ED. That's what you need to know. Same applies with the rectangles. You need to know the properties of the rectangle, that the opposite side of a rectangle are equal and parallel. And then opposite angles of a rectangle are equal, and they're always 90 degrees. That's all. Same apply with the rhombus. You need to know those properties of the rhombus. You need to know those properties of the square. You need to know those properties of the trapezium. You need to know those properties of the kite. Then now let's go to the fun part of Euclidean geometry, the most interesting part, my favorite part, I think, which is the basic circle terminology. So we can see in this diagram right here, we have got tangent, we've got secant, we've got diameter, we've got sector, we've got the radius, we've got a chord, we've got segment, we've got an arc. you need to know that terminology. You need to know the definition. You need to know what is meant by a diameter. You need to know what is meant by a tangent. You need to know what is meant by a chord. So a radius is a line from the center to any point on the circumference. That line is a radius. And the diameter is the line from any point on the circumference. Passes through the center, just like we can see this one, that a diameter starts here at that point on the circumference, moves and passes through the center, moves to that other point on the circumference. That's the diameter. And then we are also going to have the chord. The chord is also the line that moves from any point on the circumference to other point on the circumference. But the difference between the chord and the diameter is that the diameter passes through the center and the chord doesn't pass through the center. That's the difference. Then we've got the sector, which is just this portion here between the radius and the arc, whereby the arc is this part that I highlighted, this part. Then the sector is the inner part on the circle, inside the circle. Then we also have got the secant, a line that passes through the circle. It passes through, or it cuts the circle. It also goes outside the circle, just like we can see here. It doesn't move from the circumference to the circumference. It goes to the outside. Then we also have got the tangent right there, which is the line that touches the circle on the circumference at one point. The circumference doesn't touch the circle at 2 points. Once the line touches the circle at 2 points, that line, if it goes outside the circle, it's a secant. If it doesn't go outside the circle, it's a chord. But if it touches the circle at 1 point, then it's a tangent. Then now let's move to the theorems. This is the theorem 1a. Then now here they are saying theorem 1 in a nutshell. According to the given circle sketched below, if OM in a circle, we can see OM in this circle. This is the circle I'm talking about, right? This one is the circle I'm talking about. So in this circle, if OM, this is OM, this is OM. If this is OM and is perpendicular to AB, and then that implies that these angles are 90 degrees. That implies that AM is equal to MB. That only applies if the line drawn from the center to this chord AB is perpendicular at the intersection. You can conclude by saying AM is equal to MB. Then we have got the converse of that theorem, that now, if it is given that this line AM and MB are equal, if now you are given that they are equal, then you can conclude by saying these angles are 90 degrees and then OM is perpendicular to AB. That's the converse of theorem 1. And then you also have to know the proof, guys, because I think it is also accessible. They can assess you to prove theorem 1, or they say show that if OM is perpendicular to AB, then AM is equal to MB. So it's wise for you guys to know the proofs. Then we can move to theorem 2 right here. We've got theorem 2 here, which just states that an angle at the center is 2 times angle at the circumference right here. Angle at the center is 2 times angle at the circumference. Meaning maybe if we focus on this diagram and then we say this angle at the center is 2 times that angle. if I said maybe to you, that angle at the circumference is x, then according to this theorem, this angle at the center will be 2x, and then that's a statement. You have to put the reason for that. Angle at the center is 2 times angle at the circumference. Same applies with this and this. You also need to know the proof, guys. It is also accessible. Then we can go for the third theorem, whereby they say the angle subtended, they say here, the angle subtended, sorry, can I please remove that, sorry? The angle subtended at the circle by a diameter is a right angle. We know what the right angle is. It's a 90 degrees angle. We say that angle in a semicircle, that's our reasoning for this theorem, angle in a semicircle. Remember what semi? It's half. So angle in half of a circle, angle in a semicircle is our reason. So according to the given circle sketched below, this sketch, if AB, this is our AB, is a diameter, we know what a diameter is. And then that implies that AC is perpendicular to CB, meaning that angle C is 90 degrees. Then it also have got the proof for you guys to go read it and practice it more and more and more until you master it. Then we can just pass to another theorem. Theorem 4. They are saying here, an arc of the chord. This is the chord that they are talking about. This is the chord they are talking about, or the arc they are talking about. Of a circle subtends equal angles at the circumference of the circle. Subtends equal angles. So these are the equal angles, or that. Just think of a bow tie shape. I think if you think of this bow tie shape, you will never go wrong in the diagram. Then you know that you're going to use the angles in the same segment reasoning for that. Your reasoning is just going to be angles in the same segment or angles subtended by the same chord or the same arc. Then you are done. For example, in this circle here, you've got that bow tie-ish shape there. Therefore, this angle X that you're looking for is going to be that angle 20. Reason being, angles in the same segment. And this angle Y is going to be equal to that 15 degrees, reason being, angles in the same segment. Then we can proceed to the next theorem. They are saying we've got corollaries of theorem 4. And then we can see when we look on this circle that we have got chords here. And these chords is given that they are equal. So this corollary is saying equal chords subtends those equal angles. And note that those angles are opposite those sides that we are saying are equal. Same applies with this one. We have got this triangle right here. We've got that triangle right there. And then we've got the chord as the side of the triangle. We also have got the chord as the side of this triangle. And those chords are equal. Just remember, equal chords subtend equal angles. Those that are equal, those equal, that are opposite, those equal chords. Same applies with this one. You've got the chord as the other side of the triangle. You've got the chord as the other side of a triangle. And then you've got angles up there opposite those equal chords. And those equal chords subtend equal angles. Therefore, those angles are equal. Then we can simply move to the other theorem. Here it is, theorem 5, a cyclic quad. They are saying a quadrilateral whose vertices lie on the circumference of a circle is referred to as a cyclic quadrilateral. We are going to use this a lot in grade 11 grade 12, cyclic quad in short. So A, B, C, D in this diagram is a cyclic quadrilateral. Why? Because point A, B, C, and D are the vertices, and they are all on the circumference of the circle. Therefore, it is a cyclic quad. Therefore, you need to know all the properties of the cyclic quad because we are going to use that a lot. So the first property of the cyclic quad that you need to know is that opposite angles of a cyclic quad are supplementary. What do we mean by supplementary? When you sum them up, they give you 180 degrees. Meaning in this case, if you come to this diagram, and then you add that angle D right there to this angle B, you're going to get 180 degrees. Those angles are opposite. Same applies with this angle and this angle. They are opposite. When you sum them up, they are supplementary. Thank you. That's what you need to know. Then you can move to the converse of that theorem, because sometimes you can be given that opposite angle of a quadrilateral. You are just given a quadrilateral, just like maybe they did in this case. They give us a quadrilateral here. And then they say to you, show that this quadrilateral is a cyclic quad. What are you going to do? You are just going to take that angle, you add to this angle. If you get 180 degrees as your outcome, you can conclude by saying that quadrilateral is a cyclic quad. It's the converse of opposite angle of a cyclic quad are supplementary. Then it has got also the proof here you need to know to go proof in the exam, because it's also accessible. And then we can proceed to the next theorem, which is theorem 6. Then here they are saying the exterior angle of a cyclic quadrilateral. Where is the exterior angle? There is the exterior angle of a cyclic quadrilateral. This is the cyclic quadrilateral. Then that is the exterior angle they're talking about, is equal to the interior opposite angle, which is that one. So this angle is equal to that interior opposite angle inside there in a cyclic quad. That's the reason that we are going to use a lot in this cycle geometry. Then we also can go to the converse of this theorem. Sorry. The converse is saying, if an exterior angle of a quadrilateral, we don't know what this quadrilateral is, but if that exterior angle of the quadrilateral is equal to the interior opposite angle, then we can conclude by saying that quadrilateral is a cyclic quad. That's all you need to know. It's a cyclic quad. Then we can move to theorem 7. It's most simplest theorem, I think. Sorry for that. My apology. Theorem 7, we are saying we have got a circle, and then we have got the tangent. We've got the tangent right there. We've got our circle. We've got the radius. Then this theorem is saying the tangent to this circle is perpendicular to the radius. The tangent to this circle is perpendicular to radius, meaning at the point of intersection, which is this one, they intersected an angle of 90 degrees. Same applies with this one. Then we can go to the converse of that. If it is given that you have got a line perpendicular to that radius, the line perpendicular to the radius of the given circle, you can conclude by saying that line is a tangent using the converse of the tan chord theorem. I mean, not the tan chord, tan perpendicular to the radius. Then we can proceed to the next theorem, theorem 8, I think the second last. So this theorem is saying if two tangents are drawn from the same point, of which in this case the same point is A, is drawn to B, the point of intersection of this tangent and the circle. Again, the line from A to C is the tangent. They intersect the circle at C. Then this is saying those are equal in length. Those lines are equal, meaning this implies that if A is extended as a line to B and as well is extended to C as a tangent, those lines AB and AC are equal. This is also the theorem. This is also the proof for the theorem. Then we can move to the last theorem of the circle geometry before we can go tackle some few questions. So we have what theorem 9 here is saying the angle between the tangent, here is the tangent of ours. This is our tangent that we are talking about to this circle, and the chord. This can be a chord. This also can be a chord. So the tangent between the angle between the tangent to the chord and a chord drawn from a circle of from the point of a contact is equal to the angle in an alternate segment. They are just saying this, in simple terms, this angle right there is equal to that angle that is opposite to the chord that we focused on. So we focused on this chord, and this chord is opposite that angle right there. This implies that this angle right here, this angle is equal to this angle. Same applies with this angle, and then we focused on this chord. This is our tangent. We go to the angle that is opposite to that chord of focus, which is this angle. Therefore, this implies that this angle is equal to that angle, reason being tan chord theorem. Then we are done with those theorem. I think now is the best time to go approach some problems. Let me see if I can just quickly find some problems here with me. And then let me just do this. And then I can go to WhatsApp. I think this one. I'll find some good question. So this is the question that I want us all to just look through, whereby they are saying in the sketch below, circle center O has the tangent KLM with the diameter NQ. And then you've got the diameter there. And then produced to meet K, I mean to meet the tangent in K, there is K out there, we can see. So I would advise you to do this. Let me see if I can be able to share to show some camera here, because I want to write something down. So can you all see now what I'm sharing now?
Yes, sir.
Okay. So when you attend or when you want to attempt those circle geometry, I would advise you to maybe on your question paper, write down this DRCPT. I just think of Dr. Cape Town when I just want to simply remember it. DRCPT, Dr. Cape Town, where this D is the diameter of the circle, and you know what the diameter is, and this R is the radius of the circle, and then this C is a cyclic quadrilateral, and this P is for parallel lines, and this T is for the tangent line on the circle. And then we have discussed this, what the diameter is earlier on. We We have discussed what the radius is earlier on. We've discussed what the cyclic quad is. You also know what a parallel line is. You also know what a tangent is to a circle. So I want you to do this when you get to those kind of questions. When you just get to your diagrams and then there's that circle, and then there are those complicated things in the circle. Before you can attempt the question, after you read that statement, you go to your DRCPT D. You look at your circle if there is a diameter there on that diagram, because you can just find something out there. I'm sorry for that. You can find out maybe if there is a focus. Okay, if there is a diameter on the circle, there is that theorem that we know about the diameter, that you can find some angle of a 90 degrees there. But if there is no diameter, you can pass. Then you've got R, which is the radius of the circle. Then you can find sometimes there can be a situation whereby maybe you've got some radii, which is the plural of the radius. This is the radius, this is the radius, and we know that the radius are equal. That implies that maybe this angle is equal to this angle. This is an isosceles triangle. The reason being angle opposite equal sides. Fine. If there is no radius, you can pass to the cyclic quad. You apply what you know about the cyclic quad. If this is a circle, and then this is our cyclic quad, and then you know that the opposite side, when you sum them, opposite angles of a cyclic quad, when you sum them up, you get 180 degrees. Same applies, check if there exists a line that is extended. You can just say that angle is equal to that interior opposite angle. Parallel lines, if there exist parallel lines, you go for your maths is fun technique. If there some parallel lines can come up with some F corresponding angles, then you state your parallel lines. You can also go for U for interior angles. Sum of these angles, when you add this and this, you get 180 degrees. Same applies with this. We are going to state the parallel lines. This is equal to this, then you state your parallel lines. Then if there exists that X that we talked about earlier on, you can also highlight, I'm sorry for that. You can also highlight those vertically opposite angles. And then you can go for the tangent. You apply the theorem that you know about the tangent, which is the tan chord theorem. This angle is equal to that angle, or the tan is perpendicular to the radius. That's all what you need to know. And then you can just go to the questions and then see most of the question will be answered by now, by that time. We can just go back to this problem and see if we can win with this question. So as they've said that they've got this circle of the center O, and then there exists a tangent KLM, and then the diameter NQ. That tells us something. If you write your Dr. Cape Town DRCPT, there exists the diameter in this circle, which is QN. That implies that angle QLN, which is this angle right here, this angle here is 90 degrees. Why? Because it's angled in a semicircle. This is the semicircle that we are talking about. Okay, we noted that. Then we go for the radius. We apply the theorem that we know about the radius. The one that we know about the radius is that radius is perpendicular to tan. But then here, we don't have the radius that is perpendicular to tan. It's fine. Then also we know that the radius of the circle is equal throughout the circle. So this line OP is equal to this line ON. Therefore, this implies that this angle here P2 is equal to that angle right there, angle N2. Reason being isosceles triangle or base of the isosceles triangle or angle opposite equal sides. Then after you are done with the radius part, you go for C in your DRCPT, which is the cyclic quad. Is there a cyclic quad here? No, there isn't. So there's nothing we can do with the cyclic quad properties. Then is there parallel lines? No, there are no parallel lines. Is there a tangent? Yes, there is a tangent. We can use a tan chord theorem, and then we can see that this theorem here, sorry, excuse me, is between the tangent and this chord. So it's going to be equal to that angle that is opposite the chord of focus. So this angle here is going to be equal to this angle here. And again, this angle is between the tan and this chord. So it's going to be equal to that opposite angle. So this angle here is going to be equal to that angle, tan chord theorem. Then we can go to the question and see if we are going to win. They are saying calculate, and not just calculate, but calculate, give some reasons. Why are you going to say P2 is this? So what is the size of P2? When we look on this diagram of ours here, we already discussed something. We can see that P2 is right here, and we have said that this angle is equal to that angle. So P2 is equal to 23 degrees, reason being base of isosceles triangle or angles opposite equal side. Then we go for 5.1.2, which is find the size of angle POQ. POQ, okay, that one, how are we going to find it? Okay, we already have this angle. This is the triangle. We can find this angle PON by saying angle PON plus angle N2 plus angle P2 is equal to 180 degrees. Interior angles of a triangle are supplementary. They add up to 180 degrees. Then you solve for that angle PON. After you got that PON, you can simply get POQ by saying 180 degrees minus this PON. Reason being angles on a straight line are supplementary. Then moving to 5.2.3, angle L2. There is L2 right there. And then we can see L2 is at the center. We had this angle at the, is at the circumference. And then we have this angle at the center right there. We go back to that theorem that is saying angle at the center is 2 times angle at the circumference. This here is 2 times that. Meaning, if you have this, you want that. You are just going to divide this by 2 because that is half of this. But reasoning is going to be angle at the center is 2 times angle at the circumference. Then 5.2.4, we want the size of NLQ. NLQ. We've discussed this. I think it was the first thing that we talked about on from DRCPT. When we were on D, we said, okay, NLQ is this size, which is 90 degrees angle in a semicircle. Then we are done with that. Then 5.2.5 is saying, look for the size of angle L3. L3 is right there. And then remember, we found this angle is 90 degrees. And then we found this angle here, then you can just say that 90 minus L2, we are definitely going to be left with L3. Then we can have the last one, 5.2.6 as PLK. PLK, which is this one right here. We also talked about this when we were talking about the tan chord theorem. saying that this angle here is between the tangent and this chord. So it's going to be equal to the angle that is opposite the chord of the focus. So this angle is equal to this angle. 23 plus 32 is equal to that angle, PLK. Then that's how you approach this kind of question, guys. With DRCPT technique, I don't think you will ever go wrong. So any question regarding what we have talked about today? Hello, guys, are you all still there? Hello?
Yes, sir.
Are you all still there? Like, I'm asking if is there any question that you guys are still wondering what we can do with regarding what we've just talked about?
No question, sir.
Or you are all cool?
Yes, sir.
Okay, then if that's the case, I think we will end here for the day. But I will just send some question to Mr. Desmond, and then he will just drop them for you into the group so that you can do as the homework. Then next time we meet, we will first discuss the corrections before we can continue to the next part of the lesson. Thank you all. Have a good night, and thank you all for working with me.